Hi, Hannu. Welcome to the podcast Everyday Metallurgy.
Hi, thank you for the invitation. It's great to be here finally.
Yeah, Hannu, you are a mix of something I'm very proud of. You have won the thesis competition of the EPMA thesis in powder metallurgy. But the other thing I'm pretty proud of presenting is that the theme you are working on is recycling of hard metal. And hard metal today is maybe on top three of critical raw material we're talking about in Europe, especially with the tungsten as a material that is exploding on price and in difficulties in deliveries. So recycling is, wow, spot on. Something we need to talk about today. So welcome with this extremely important theme. Hannu, will you give a short introduction to yourself?
Yeah, of course, thanks. So, I'm a research scientist at VTT at the moment. So VTT is a Technical Research Centre of Finland. And in 2 years ago, a bit past, I graduated from the university, actually across the street. And I studied materials engineering as my major, and also during my master's thesis studied machine design and sustainable materials as minor studies. At VTT, I started first as a summer trainee about 3 years ago. And a bit after that, I started doing my master's thesis for VTT here at the same location. And and since 2025, I've been working here as a research scientist after finalizing of the thesis.
Perfect. You won this EPMA thesis. Can you tell a little more about what is that? How do you participate, and why did you choose to participate in that?
Yeah, so the competition is organized by the European Powder Metallurgy Association, and basically you can apply for it through the EPMA's website. There are some rules for that. You have to be graduated in the recent times and things like that. They are all written somewhere in there. And there are separate categories for master's thesis and PhD level thesis. So there is some kind of international panel of experts in the field of powder metallurgy, judging and evaluating. So basically you are sending there of course, the thesis itself, but also an extended abstract of your thesis, and something else. It's also written in there. And actually I think it was my boss who first mentioned about this competition, and we also in our team we didn't have previous experience about this thesis, but we decided to try it out, and it seems that it went pretty well, and
that's why you're here.
I guess. So I won the award, and I got the opportunity to participate into the European conference. It was held in Glasgow last autumn, and it was a really nice event and opportunity itself.
So the prize was a free participation in an international conference?
Yes, and there was also cash price of 500 euros for master's thesis and 1,000 euros for the PhD.
I want to make a new thesis and apply.
Yeah, you should try.
Yeah.
And I also had an opportunity to receive the award there on the stage and give a brief speech about the contents of my thesis to the European audience.
Exactly, yeah. So, what was the project about? Let's dive deeper into it.
Yeah, so the thesis itself has a title of Granulation of ready-to-press powders using recycled tungsten, carbide, cobalt, and simulation of powder behavior. So, in brief, I would say in the beginning of the thesis, in the theoretical part, I studied basically the effects of particle level properties on powder properties. So these different things like size of particles, particle size distributions, shape of particles, environmental effects, compressibility of granules in this case, and things like that, and also the different granulation mechanisms, how these work. So this work was basically about spray drying and these high shear mixing processes to make these so-called ready-to-press powders from hard metal.
I need to understand more about where is the recycling. Where does the powder come from?
Well, the exact powder in our case, it actually came from a Finnish company here, which does this zinc recycling of hard metal components. So, so maybe shortly about the zinc recycling process. So basically, the hard metal scrap, which is used as the raw material for the recycling, it comes from different sources, but it's mainly like different kind of cutting inserts, drill bits, wear parts, some kind of machining tools usually. And when they are at the end of their life, they can be recycled, and this zinc recycling is concerned as a good way, environmentally good way also to recycle these components. So it's basically it's hard metal scrap, and zinc is put into a furnace, and the zinc is melted at several hundred degrees, and the zinc reacts with the cobalt binder in the hard metal components and creates this like a intermetallic compound of cobalt and zinc and so on, and then the zinc is like vacuum distilled kind of out of the components, and it leaves behind this brittle component of hard metal, which can afterwards be milled back to the
so it's like cornflakes. You can just crush it.
Yeah, basically, and but it still requires like intensive milling.
Okay.
It's not so like brittle and soft and weak, but
hard cornflakes.
Yeah. Basically, yeah.
Yeah. So it's milled into particle size. What level are we talking?
Well, we are talking about maybe some microns, depending on the grade. Of course, they have some different grades that they are producing and so on. But for example, in our case, I think it was below 5 microns, the size of the raw material powder.
And then you said you agglomerated, and I understood you were going to compact it, to press it uniaxial. Why is it necessary to agglomerate it prior to compaction?
Yeah, well, I think there are several reasons for that, but at least one point is that hard metal powder, it's really hard. So basically, if you try to compress it just by itself, it doesn't do anything. You can't have a green state product. So it first of all requires some kind of a binder, usually some kind of a polymer or paraffin wax binder, and then why is it agglomerated or granulated? I think one reason is that because of the mold filling properties. So if you have, for example, a small mold or a mold with some smaller cavities, then this very fine powder, which is not nearly spherical, for example, it has very poor flowability, or it doesn't flow that much. So it doesn't fill the mold properly. And when you try to compress the powder, these granules make it so that the density distribution in the green state product is more evenly distributed. So you kind of, with this granulation, you want to have increase the packing density of the powder, for example. So you want to have dense granules with spherical shape as possible, and with reasonable particle size distribution and particle size. And maybe one reason is that it's much easier for the transportation of the powders. For example, in the production sites, you often have some kind of silos or hoppers of some kind that you want to flow the powder through. And it's much easier with these granules, and it also reduces the dusting of these powders when they are kind of binded with a polymer.
The dusting leads to the question that there's cobalt in the powder, and cobalt below 5 micron, is that a risk?
I'd say at least at some level, yes, of course. So especially with cobalt-containing fine powders, it's considered toxic when inhaled, especially. And you know that in the industrial settings, this exposure to these cobalt powders, and these are monitored some way, but there are luckily some ways to reduce these risks with some proper safety measures. So to name some, at least the ventilation of the production site should be at good level, and then there are different kind of dust control systems where you can monitor that which kind of processes are the most critical concerning these fine powder dusting, and then you can make something to reduce that. And of course, the personal safety equipment is always the first thing to look after. But and the long-term exposure, at least at the production sites, there's a reason for the monitoring of these things, but at the same time, at least from our perspective, when dealing with all kind of metal powders and so on, so that's pretty much the same thing with all metal powders, fine metal powders. So you always have to be concerned about these things.
Yeah,
basically.
Yeah. Then if we jump back to the agglomeration, you add a binder, and do you also add lubricant, or are there additives that are used during the sintering process?
The polymer or the binder itself, it's also acting as a lubricant, basically. So at least, yeah, most of them. So no need to add like extra lubricating materials there. But regarding the additives for sintering, I would say that regarding these tungsten carbide cobalt products, I would say that there is this ether phase formation, which is a common thing for hard metal components, which it's a compound between cobalt, tungsten, and carbide, and it basically forms due to the lack of carbon in the structure.
Yeah. So, is that a liquid phase during sintering?
During sintering, yes, I would say, because the sintering of hard metal components, it's a liquid state sintering process. So basically the cobalt binder is at liquid state, and the temperatures are around 1400 degrees Celsius.
That's high. So, is it an argon or active atmosphere?
It depends. Argon, yes, it's a common one. Also vacuum. Vacuum sintering is common for these, or some kind of argon plus hydrogen, mildly reducing atmosphere might be. So regarding the question, the carbon balance is something that is crucial for these hard metal components to prevent that ether phase to forming. So it's a brittle phase, and it's not wanted for these applications of hard metal components.
So what is a potential application for a component produced via this route?
Well, basically the recycled powder itself, it's the properties of components made of recycled or primary raw materials. There is not much of a difference, or it's hard to tell the difference.
Okay, it's on par with virgin material?
Yeah. So it can be very well used for new cutting inserts and machining tools and so on.
You don't need to downgrade to dubs in winter tires.
No, you don't. No. You don't. Yeah, it's we have actually a bit studied about it in the past year, but it seems that it's hard to make conclusions about it, because it seems that there is also some other thing that is more like important for the mechanical properties, for example, than the fact that is it recycled or not. So I would say that it's a good, convenient way of recycling hard metal components and obtaining good quality powders.
Yeah. Do you know if there is an existing collection of used hard metal components in Europe today?
I don't know exactly, so, but yeah, I don't know exactly, but
after
yeah,
hearing this, might be because if you if you can use it as a raw material and remanufacture to a powder that creates components with same properties as virgin, it could be an extremely important flow stream in our European supply chain.
Yeah, and of course that's what we want in Europe and want to increase. And and I know that some companies providing these hard metal tools, for example, they're like collecting back those products after use. So they are not like, because they are very valuable raw materials even after the use. So that at least I know that is happening for some of those companies.
Yeah. Hannu, in your project, you also looked into a simulation method called DEM, where most are maybe not familiar with that way of analyzing or simulating. Can you give a short insight in what is DEM and what do you use it for?
Yeah, sure. So yeah, that was also quite new topic for me when I started doing the master's thesis. So and a fairly new topic in general, but I think there is more interest coming in all the time, and I've noticed that new these simulation software providers are making their own DEM softwares all the time. So, but maybe to give a short introduction, I think more people are familiar with this finite element method simulations. So with those, we have some kind of a component, and we have a digital 3D model of it, and then we want to calculate, for example, stresses that are acting on the component when it's under some sort of forces. So how this is basically done is that the component is meshed or divided into finite amount of tiny bit of elements. These tiny fractions of elements.
Small voxels or 3D shaped triangles.
Yeah, basically so, yeah. And then for example, forces and deformations and or heat flow or things like that, they are basically calculated and distributed through these small elements, kind of one by one. So that's what finite element method is generally about. When on the other hand, this discrete element method, it's not usually used for components, but it's used for granular materials usually. So different kind of powders or sand or rocks or different kind of granular materials. And here, instead of meshing these particles itself, these particles are actually like the elements itself, kind of in the discrete element method. So it the model actually calculates the position and movement and trajectories and interactions with other particles each time step for every particle in the simulation.
Yeah. So if I have two particles here,
yeah,
if they are in an FEA and you make a deformation that goes like that, the FEA will break.
Yeah.
Because your voxel is going negative. But in your case, you can move the particles around. Is that how I should understand it?
Yeah. Yeah. When talking about deformation of particles, or if we would be interested in deformation of single particle under compression, for example, that would be a simulation for a FEM study, I would say. But when we have a million particles, for example, we have a small pile of powder, then the finite element method is not working. You cannot mesh these million particles and calculate all of these deformation of every particle and so on. So with this discrete element method, you don't need to have this meshing thing for each particle, and actually the deformation of these particles, at least in my example, the particles, even though it looks like they are deforming or the powder bed is compressing, the powder particles itself are rather penetrating each other than compressing or reshaping during the compression. So it's a more efficient way doing this. But even
so
with
you simulated the compaction process itself of the agglomerates.
Yeah, basically. Yeah. And it also has some limitation or challenges with the case I had. So the usually discrete element method is used for different kind of conveyor systems, or study mixing of powder, or segregation of different kind of particles, or even breakage of particles in some cases. But the compression of these particles, it's a bit more challenging, and I would say that with my master's thesis study, I think I jumped right into the deep end, kind of with the compression of these particles at the same time. So it was quite challenging, and
it's also a big piece of work looking into in the master thesis. I know people who cannot do the same in a PhD thesis. So,
yeah, I'm sure. Yeah.
Hannu, you finished your thesis, and did you get a job based off the thesis? And do you work with the same methods today and the same products at VTT?
Yeah, pretty much. Yes. So, yeah, it's the same team. I started as a research trainee or summer trainee like 3 years ago. So basically, I just continued from the master's thesis to other kind of projects and things and so on. But maybe briefly about what we do here, what I do here. So our team is called Sustainable Materials Design, but we basically focus on metallic and ceramic materials and their material development in the field of powder metallurgy. Very broad field of materials and ways of handling those. But maybe as an example, we have this kind of a workflow for a certain project that we might have. So we can start from elemental raw materials, and we have a gas atomization device here, so we can generate a certain powder of a certain alloy or just pure elements, and then with this we can move on. We have many kind of different forming techniques for the samples. So one thing that is very common for us nowadays is the direct energy deposition powder 3D printer, which has been used a lot for different kind of, well, it's perfect for our alloy development studies, so we can in situ monitor the alloy composition basically with that. So it's very handy. 10 other techniques to name some: HIP, hot isostatic pressing, hot pressing.
Yeah, you have your own HIP?
Yes, we have. Yeah.
I would like one of those in my garage as well.
Yeah, I'm sure many of us.
Yeah.
And of course, conventional pressing and sintering of samples at different atmospheres and so on, and of course characterization. So, for example, XRD phase analysis, SEM, mechanical properties of these samples are something, some, let's say, daily used things in our team. So quite broad range of different kind of materials and applications.
Yeah, wonderful. Thank you. I have a last question because this is we're taking the offset in the thesis competition. Would you recommend other young students to participate in the thesis competition?
Yeah, of course, I would. It was at least the opportunity to go into the participate into the event itself. It's worth some hours to put into the writing the abstract and all the additional features. It's not that much of a work, but I think it's very well worth the effort, and little cash prize always motivates, and
but the biggest prize is that you were invited to talk about your project on Everyday Metallurgy.
Yeah, of course.
Yeah. Thank you. Yeah. And do you know when the window is open for next call for the thesis competition?
Yeah, I think it's actually open at the moment. So I don't know if it was until April or May, the deadline. I'm not sure, but yeah, in the EPMA website, I'm sure that it's said there.
Yeah, I will go have a look and share that with the audience in this episode.
Yeah, of course.
Yeah. Hannu, do you have any more to add?
No, I don't think. Yeah, I think that's pretty much about thesis and what we've been doing.
Wonderful. Thank you very much. I enjoyed it. I learned something new, and I think maybe you were lucky that you just hit on the top of the nail when you took recycling of hard metal at that time, because it's you said 2 years ago today you started the project, but the actuality today has never been bigger than it is. So spot on. Thank you.
Yeah, I think so too. Yeah.
Yeah.
Thank you. It was a pleasure.
Yeah. See you.
Yep. See you.